Hello, my name is Nikolai Gotti. I work at NEAR and on the contract runtime, and would like to introduce you Ethan Frey. Ethan, tell us somewhat about yourself and what you're doing.
Cool. Yeah, my name's Ethan Frey. I'm the founder of CosmWasm. I am coming from Cosmos, if you've heard of the Cosmos IBC blockchain, and worked on that 2017, 18, some other projects around it. And in 2019, got really excited about smart contracts. So started looking at that. So yeah, since summer 2019, I started a project called CosmWasm, which is WebAssembly, WASM smart contracts embedded in the Cosmos SDK. So it's basically all the tooling. There's Go blockchain, so like Cosmos, it's basically a construction kit. And then we're embedding WASM contracts into that. So actually I can answer all the questions about the Tendermint and SDK as well, because I spent time working on that ages ago. But all I'm working now is basically the runtime. Of that, the bindings to the contract and then the contracts themselves.
Okay, and I think there are multiple blockchains supporting WASM contracts. So what would you say is differentiating CosmWasm out of those?
Our biggest differentiator is we're not a blockchain.
Okay.
I think that's key. People ask us what's a blockchain. Maybe we will someday. But we are effectively a platform or a module to integrate into other blockchains. So what Cosmos' idea is, these people rejected Ethereum maximalism, everything around Ethereum, and said rather than having one chain to rule them all, which was totally impossible in Ethereum in 2016, 17, let's do a network of blockchains and connect them the same way the internet scales horizontally. So that's where it comes from. So what you have is you have a bunch of people building application-specific blockchains. So their code. The problem is writing a code, the hard forking for every upgrade is kind of tedious. You just can't upload contracts, there's issues. And smart contracts were a cool idea, so I added them into these. There are currently, I think, six blockchains in the Cosmos ecosystem that integrated our module into theirs, which means it runs inside of 5 or 6 blockchains, currently in testnet. But yeah, it's running there. I think NEAR took a different approach. They looked at Ethereum and scaled it vertically. So you guys actually broke a lot of the barriers of 20 transactions a second by making one chain that can actually scale up to real world speeds. So we've gone horizontally, a bunch of smaller chains that have decent throughput, and they're connected horizontally over IBC into blockchain communication.
Okay. And is CosmWasm aiming to public blockchain only, or you also want to connect private blockchains like Facebook, for example, Libra product?
Yeah, so that's a big question. Right now we're looking at public blockchains because that's what I've seen. We've looked at enterprise market. I think there's a huge market there actually, and in some way a business opportunity. They can use CosmWasm. It's open for them to use. It's Apache. And if someone wants to, I think we're not going that route ourselves because that's a lot of the private blockchain market requires different expertise. It's enterprise sales. I can sell to startups. I can't sell to enterprises. I can sell to devs. So we looked at that, and currently we're not looking at that. We're very happy if someone else wants to integrate into those private chains. They're welcome to. Please talk to us.
Okay. Yeah. And so if you want to integrate like a multiple blockchains in CosmWasm, I think they usually have their own like runtime for execution of the contracts, including a custom set of host functions. So, for example, in case of WebAssembly, it's indeed a portable standard, so it's probably okay if you can execute the contract. But how do you emulate the behavior of the particular blockchain?
You're right. We kind of don't admit an abstraction layer. So the funny thing is, Cosmos SDK has one thing I really don't like about it, which they change. They make backwards compatible changes like every 6 months. But that's a good thing too, because we have to use supporting different versions. So we said quickly on the same contract that runs in 0.37 should run in 8.9.40 of the Cosmos SDK, which has either minor to major changes. So we can't use their native functions directly. So we had to make an abstraction layer between that. So what we currently do is we have abstraction for sending messages to other modules, which can be other contract or native modules. We have an abstraction for querying other contract or native modules. And we have a storage, local storage, and we have an API, which are basically precompiles. So what you can do is basically offer a fixed set of functionality, which you've standardized more or less, which is the bank module and the staking module, a lot of the POS chains mostly. So, and when you call into it, takes your message from the contract, converts it into the native message format, calls into the native code, takes the response and converts it into the contract response. The same contract could run 3 different chains, possibly with different versions of different staking modules, as long as they have an interface. So we define a common API, basically, that the change must implement. And that's also limited because we didn't expose extra. And we added in recently, about a month ago, because they're trying to integrate into a native chain that had its own swap, kind of Uniswap type, and Oracle treasuries type functionality. Don't expose it. So we added a way of extending it. So basically, we pass messages opaquely through our runtime. So if you want to extend your blockchain, your runtime, you can add handlers for different message types. And it's a custom message type, which is basically this raw bytes you can then pass on to your blockchain, interpret it. And we allow custom messages and custom queries, which means you basically have you have a Rust binding, import a Rust library. It says, give you these extensions, and you have the extension APIs. And it also has a feature flag saying, okay, this contract only works in Terra, or only works in Regen, only works in Enigma, because we're using these custom bindings. And then their blockchain handles those custom bindings. So you can write a portable contract using the standard set, which runs on all chains, or you can make use of custom features from that chain, but then you opt into them, and your contract is only chain specific at that point. It's a bit of I can go into details on that sometime. It's a bunch of Rust generics in there, and then serialization and stuff. But yeah, it actually works pretty well. So you pass it basically from the WASM, cares about the format of the queries and messages, and then it takes everything to bytes. It passes all the way through our virtual machine into a Rust binding, into Go library, into the Go blockchain, through about I think 3 different packages into the end user's code is not ours, and that then actually has a handler for these bytes to then handle them. And so basically input that on both in your personal app and on the contract.
Okay, so it means you generally want to provide servers somewhat similar to what we have in a standard like virtual machines, like in Java, for example, when you can run the same Java application on multiple operating systems by commonizing their porting layer into some least common denominator.
Yeah, exactly. And you also allow using JNI to access the custom stuff with Java too. So wonderful. Actually, ideally, like I will, if let's say 4 chains all using some variation of Uniswap, I'd love to make a Uniswap standard and opt that in, and they could all implement this Uniswap standard to the same, contract could use Uniswap depending, not caring out whose kind of Uniswap implementation it is, and whether it's a contract native. So that's something I'd like to kind of go towards. But right now, we just standardize the basic ones, which is moving tokens and staking.
Okay, yeah. I guess the selection of the language for writing the contracts, especially in your situation, became very, very interesting problem. So what do you think about that? So do you believe that like Rust rules them all, or there should be multiple languages, or there should be some other language which is default? So what's your opinion on that?
Well, I started with Rust because the tooling. I had to learn Rust anyway for the tooling for Rust and WASM is really awesome. And I actually learned Rust on this project. I mean, I dabbled in it before. I'd written like hobby projects, but never done a real project in Rust until I started working on this in a hackathon, actually, coding it. Luckily with another Rust dev. But yeah, so I find Rust cool. I've really grown to love Rust. I think it's an awesome language. but it's not for everyone that has a learning curve. So I think maybe everyone will eventually get there, but I don't expect everyone to go there tomorrow, right? And um, I hear a lot of people wishing to have, so Cosmos SDK ecosystem. A lot of people program Go, and they want Go. Other people talk about JavaScript, or they want Kotlin.
Assembly
So
script.
yeah, I'm actually, we were very inspired. So we saw Parity first, their stuff as well. Rust, they saw Near Protocol like, I don't know, last August or September, and saw they had assembly script working, and like as a first class citizen, and I was like, that's awesome. So I've tried a little about this stuff. It's and it's a very nice set you guys have. I was very impressed by all the work you guys are doing, and taking user experience, dev experience as like the major point of utility. So I'm very inspired by that. So we are actually planning to add assembly script some point, and Go support as well. There's apparently a subset of Go called TinyGo, which compiles the LLVM and makes WASM code. We have prototyped out minimal proof of concept. It does do a job. We'll see how much we can logically put in there. But yeah, it's definitely a plan of ours to add more languages.
Uh-huh. But I think generally like very serious distinction between languages lies in the area of automated or manual memory management. So if language semantics assumes automated memory management like Java, Kotlin, JavaScript, uh, implementing it on a current WASM runtimes may could be very non-trivial. So, so do you believe that there is a place for languages with automated memory management in a smart contract world?
Well, I think there's three ways of handling it. The first way is don't care. And you say, we throw away the contract every time, right? So during one running of a contract, you probably don't claim that much memory back, right? Like if you run 100 times and you allocate, but in one, unless you're really doing something weird, you probably don't keep allocating 50K, free 50K, allocate 50K, free 50K, and somehow manage to use 30 megabytes of RAM by accident because you're just in a deep loop in a WASM contract. So if you make a clean, fresh instance every time you run the contract and throw it away at the end, it doesn't really matter, honestly. It's not WASI, which actually keeps long moving processes. These run in a millisecond or two. They shouldn't use that much memory. That's the cheap answer. The second answer is um, uh, theoretically they're adding some sort of support for garbage collection memory manager in there. You could compile it in your contract itself, make it huge. You actually can have a garbage collector in your contract, right? Like you can do all that, keep counting, and you have the access to all. So you could kind of, you could kind of do that in your contract. Probably hard, or you can wait for WASM to add support for the VM for that level. So I definitely prefer having Rust and say, okay, cleans up the end. I know it's great, but I think definitely people want useful languages. They want to not worry about garbage collection. They don't want to write C. They don't want to write Rust. They want to write something easy, and so I think it's our job building these runtimes and building these to figure out how to do that, and whether it is just clearing your memory out every time you run a contract, or whether it's somehow adding stubs to the garbage collection. That's our job as blockchains.
And yes, actually, your first answer is very tempting, I'd say. So, like, it's in many cases, indeed, everybody know that GC is not probably the most straightforward technology in software engineering. So, if you can avoid it by just not doing that, it's looking indeed very much attractive. Mm. But what's interesting, like consequences of that action is the limitation of the nature what the smart contract is. So it's it inherently becomes like very computationally limited. So it cannot have essentially unbounded allocation and deallocation inside of its evolution. So we essentially put certain limits on a computation happening inside of a smart contract. And do you believe it's a good thing or bad thing?
Well, I think it's really good. You want to limit everything in there. So, I mean, since a smart contract has to run on, I don't know, 20 to 100 machines in parallel and it blocks everything else, but, well, maybe Near doesn't. Maybe run in parallel. That's awesome stuff. But right now, we're basically in the sequential model. You process one transaction, next transaction, next transaction. And since you do that, you have to bound it. Like, we cannot have a contract running more than, I don't know, 5, 10 milliseconds. Really. If we have contracts running 10 seconds doing stuff, then the whole blockchain for 10 seconds, which is not cool, right? So by the nature of having a sequential blockchain, this linear history, we basically have to have everything, native or smart contracts. All code must fit under certain limits. Um, I think WASM outside of that context can do a lot more. And actually, the more I get into it, the more I see the potential of WASM, not just in the web and not just in blockchains, but everywhere. So WASI, for example, system interface is like kind of this. I see the alternative of Docker in a way, right? You can have these sandbox objects, which is to have a very clear interface of what syscalls I can use. So it's actually really cool. And if you're building stuff like that, you need to have garbage collection, or you need to have um, automatic memory management, like in Rust or C. So I think that case becomes really important. And so I see the kind of the binding, the conjunction of that come together in off-chain workers. I know Parity has that term. I use that term for them, off-chain workers. So basically, a blockchain triggers a task to run, a WASM task to run. It runs in parallel and it returns a result after, I don't know, 1 block, 2 blocks, 3 blocks. So you can do a long-living task that runs in parallel to the rest of the transactions. And actually, maybe you can tell me a little bit more Near, because I think Near allows some sort of parallelization like that as well. But when you start allowing that parallelization, and you no longer have to limit the code running time to 10 milliseconds. I mean, you say, okay, this can run for 1 minute. That's fine. This code can run for 1 minute. And when it's done, it'll submit the result. And when all the nodes have finished running this code, it'll submit all the results back, and we have them, and we guarantee it's correct. Awesome stuff. Great stuff. So that's
Yes,
a really
yes,
nice
that's exactly
extension.
what
Yeah.
like the direction I was heading. So, like, if we talk about the smart contracts in their current form, then I'm like raise two hands to support no memory management and stuff like that. But if we actually will think about stuff like smart services and essentially open web as and smart services as a technology supporting that, then it probably means that what we think about like a very short time span and very primitive logic inside, which is applicable to classical smart contracts, may not be really appropriate. So, so the question is probably more like not even practical, but more like strategic in a sense. So how do you believe will we need in a foreseeable future smart services or smart applications which run for relatively long time, need relatively significant amount of resources, and be able to actually um, perform theoretical and bound computations?
It's a very good question there. Very good question. I think I look for examples now, and I think there's things like running Redis in WASM, which does the work, right? And it's also in C, handles it. Um, I think there's two levels, and the first level is like you're trying a smart contract platform is trying to make it easy to write some code and deploy it, right? So I think one of the big goals there is to make a barrier of entry, the developer work, to lower that amount. The barrier to entry should be really low. Um, and we're achieving that, I think, quite a bit with we're achieving that quite a bit by adding other languages, by adding assembly script, adding Go. You know, if Kotlin is supporting it, that'd be awesome. One day, I think a few of us have been looking at that one as well. Still in development. But I think that's great for making people use it. But if you want to write real services, still, you're right. I think you're basically stuck with Rust or C to write real long running services. And stuck with is not necessarily a bad thing, but it's raise the bar of entry. And so one really concrete example I can think of is running, for example, light clients. So if you want to run these in a browser or anywhere else, that's a lot of logic. It's a lot of signature validation. a lot of math, SHA hashes,
Mm-hmm.
trees, creating trees, subtrees. It's a lot of crazy stuff, and a lot of the code we have is available in Rust. So there is like some in Go and some in Rust on our level. I think in yours all Rust. Paradise will have Rust code as well. So this is quite available in Rust, and you can port that into some smart contracts. So whether it's running in your browser, whether it's running in some smart service, which is Sandbox, that's awesome. And those pieces, I think, would have to still be written in Rust for now, in the near future at least. And in the future, they'll add maybe better garbage collection, better language support for other things. But I would basically say for one-off smaller things, open it for everyone to try it, use Wasm as standard. And if you need to use things that are not in the standard already, I would just stick with Rust for that. So I still want to make it a first language. It's my first choice of language for coding. And I definitely think the majority of developers will probably not be on Rust in 6 months a year when they see an alternative. But yeah, I definitely want to have the more direct contracts in Rust.
So like, what was your other language before Rust? I'm just curious.
My last one is Go, which is boring actually after a while.
Go. Okay, and probably before Go it was something like C or C++, right?
I started with C in university.
Oh yeah.
And then went to Java, like C, C++ as university. Well, C was like build data structures in C, right? Do everything in C, and so like messing around with Linux stuff, or back then, late '90s. Then there was Java, and then in like the mid 2000s, I discovered Python JavaScript, which was cool for hacking out websites because that was basically the work you were doing then in the late noughts, early tens, and quickly hit the limits once you started building real services on there, right? Like 2012, 13, 14, you start like scaling up services rather than just little like websites, and you're like, this doesn't work anymore. So from there I went to Go. And yeah, I played with Rust, I played with Haskell. I definitely played them before. And Rust is the one that attracted me most. It had like the type system of Haskell, which I loved, but not this like reading from disk is some weird IO monad that is like non-normal operation. You can't consider it like that's really normal. Like you can't say like interaction outside the world is not acceptable. Like this is such a special case. Like no. So I think Haskell's wonderful doing math, but like it definitely seems special case. Reading from disk should not be a special case. So I love Rust because it gave me like all that power. I love the type system there.
Actually, my background was also mostly like C and C++ and other low-level languages, and so for me, getting used to Rust was like a breeze. It's just a better C++ in my in my head. So in a sense, it's I think indeed depends on a history, on a trajectory of the person as a programmer, and so. But I guess as for many people, the trajectory is actually starts, so at least very seriously interacts with web programming, where it's typically like a JS or PHP for server side. For them, probably high-level languages would be more natural. So that's I agree. Okay, then. So if you talk like about promise of CosmWasm, so why do you believe in the fact that relatively limited set of primitives? I think you mentioned like send message, receive message, and local storage, and that's about it. What's present? Why do you believe it's sufficient for writing non-trivial contracts? So.
Well, I see. Well, basically, I think message passing. Asynchronous message passing is sufficient to build everything. And in fact, we can kind of reduce our entire distributed systems into asynchronous message passing if you actually rendering them properly. They reduce synchronous message passing, or like basically RPC calls, and have all kinds of errors because actually believe that messages come back in bounded times and promises actually resolve sometime. Yeah, they believe anyway. But if you go to this is back to distributed systems design, asynchronous message passing is the fundamental of basically all distributed systems. The actor model has also been used heavily in building large-scale systems that are supposed to be like loosely coupled. And it looked inspired not just in like what the Ethereum do, because they did a great example, but you can't copy them. I think they paved a beautiful path, Ethereum. but they also did it with a bunch of assumptions. They made everything simpler. They made their way, and they made their way. So as we scale up to larger, more complex applications, what can we do? So being able to pass messages between contracts in some asynchronous way, and then the actor models is basically you have your own state. You know, where other state you can do everything. It came to be a limit, and so the limit we hit briefly was you want to query something. So if I want to know my balance, do I have to send a message to query the balance, stop my transaction, at some later time I store the fact that I'm waiting for this message, another message comes back, and so it's just being too hard. So triggering, so we actually said, okay, I made an exception and we're going to allow queries synchronously. But I think it's fine because, which is kind of a break, is actually record everything on one chain. Before that, it was basically much more fluid. But I think it's basically what you have. You have a bunch of processes sending messages back and forth. And you know they've built huge telecoms on that, the actor model. That's all it is.
Okay. But if you think about blockchains, there are typically at least two very important operations which I don't think naturally match to message passing, and one is essentially identity management, so that you need to understand under which account or like address or whatever you execute your contract. And another one is the gas handling, so like attachment to execution certain computational resource cost. And those operations are not like they're very unusual. Not like first is normal for computer science, but I think second one is somewhat unusual for the computer science, for computation to actually attach to it its computational complexity. But generally, both of them I think crucial for execution of smart contracts. So how do you handle such problems in Cosmos?
Well, you're right. There's a lot of things. So the first part I didn't mention at all is actually one thing we exposed. We don't expose callbacks. We expose an environment object, which has the message sender, the contract address. It's the block height, the block time. I don't know. One more thing, I think. The message, if any funds are sent with the message, if any native tokens are sent with the message as well. So a little bit like what is your environment, what's your context you're called in. It's a read-only variable. So the structure can read it. It's not even callbacks, just pass it as like data. Here's this data, parse it, and this is our context. So we give, of course, a context you're running in. That's a very common concept everywhere, I think, to have, languages. So give this context, tell you who's authorized, what user is running this. The other gas handling should be opaque to contracts. They should not worry about gas handling. They run out of gas, they don't run out of gas. And it's up to the caller to worry about that, and the runtime to worry about that. So I don't think contracts should have to worry about gas. And they definitely should not have their safety depend on the fact of whether or not they can predict a gas limit for dispatching a subcall, and predictably have the gas limit for the subcall to be high enough to run correctly, but not enough to avoid reentrancy. And so a large portion of Ethereum contract security is based on the fact that you're basically well aware of the current gas and able to manipulate limits of subcalls. When you when you send a message to another contract or call another contract, you limit its gas so it can't hurt you, which I think is a detail you should not have to worry about the contract developer. So the runtime should make sure that the contract can't hurt you, basically.
So you believe it shall be handled like partially by just read-only variables in a context, and maybe partially by native for the blockchain part of the contract. Is it about right or not exactly?
Yeah, I mean, I think I don't know what context needs to go inside there. So you could ask more context, but like if people decide they need to know the app hash of the last 3 blocks in their environment, like you probably need some custom callback to that one, right? But and they can query back in the blockchain. That's a query thing. So you have this query. Besides asking messages, sending messages, you have a query, which can query anything, query current state. It's a read-only thing. So we pass these kind of standard messages, which is the block height, type, who sent it, what's my contract, who am I, right? Who am I? And the query then can query into whatever anything else. And you could have a handler saying, show me the last 3 block headers. And that could be a custom query you add. It only works in your blockchain. I don't know what else is really needed there. So when I get to composition, so if you think of this composition, I got into this and started building larger contracts. So we start getting things. I have a multi-sig contract that wants to call into to a governance voting contract that will then dispatch votes into decided to stake funds, for example, right? So let's say we have a staking derivatives contract, and so that actually is owned by someone else. So all these things just started building together recently in the last month or so. 2, 3 contracts tied together, how they do it. And that, adding out the query thing, calling back was really important to add that. So you could actually, find out the state, show me all the validators. Before I bound to validators, show me all the validators, and then you can pick one of those and then do a bound to validator as my the one of the highest, best rewards, the one I bind to, right? And so your logic can be there. Find the best one and immediately just dispatch a message to do that. And that's enough, really. Like, I'm still working on a good framework to do it. Right now, I do integration test at the high level, at the very high level, which is kind of, running the blockchain altogether. So I'm trying to figure out how to unit test integrations like that. That's currently, well, I have ideas. It's still a work in progress. So it needs to happen. But I haven't found issues. Like, the most I've tried to figure out, the current one I'm working on is callbacks. So the way I do it is different. I should like to hear Nir's explanation a bit more here. We explicitly avoid reentrancy. So we pick the actor model to avoid reentrancy because, well, 60% of all Ethereum attacks are reentrancy. And so let's just get rid of reentrancy. So, force people to think a little more firsthand, which means reentrancy basically is my contract A calls contract B, but has state in memory, not in disk, right? And then contract B calls back in contract A, reading the state of disk, which is different than state in memory, right? So let's say I have 100 tokens. Okay, I lower the memory by 100, raise your balance by 100 in memory, and then call some other contract sending it to it, right? This one calls back again, says send my 100 tokens again, and lower yours. And it keeps doing that, and everyone sees that, and eventually just write my 0 from my balance, and have now incremented 10 different balances, each by 100 tokens, and then just have a 0 in my balance. So that's reentrancy in short. So it's really tricky. And so basically the way to avoid it is save all state before you call out. So when they call into you, they only see everything you saved. You don't have a different memory and state when someone else calls into you. So we did the actor model, which forces that basically. So before, when you are modifying state, you have to persist all your changes and return a message. And the message will be dispatched to another module, and it can just change state. So only they can't change state and call into you while you're changing state. Only one thing can change state at a time, and you can't have a call depth. So using that model, it works pretty well. Most things can blindly be it. And our rehandling is if the message failed, revert the transaction. If it exceeded, keep the transaction. And that works pretty well. The failure mode is, you usually don't need to know what happened when you dispatch it. You just know it worked, right? The failure mode is right here. If contract A, in the construction of contract A, wants to create a contract B, let's say I want to create a token contract. The token contract wants to have, I'm the minter of the token contract, right? So I said the minter, I create contract B that has a minter, right, of me. But this token A needs to know who the minter is. I can draw this on a whiteboard better, probably. And that's just kind of callback thing. Yeah.
I just want to say that maybe to explain it better, you can use whiteboard. That's the whole purpose of like having whiteboard.
Cool. So let's do this now. Let's go to here. So this is actually, I think, a very interesting one, and I'd love to hear here. So we have I'll pick a few colors here. Hopefully not too ugly. And so usually we basically just say, this is some sort of DeFi contract, yeah? Swap contract over, market contract. And this is some token contract, yeah? So usually what happens is if the DeFi contract says move money, it will just say, this is fine. It will go, this is what you handle properly, I guess. And it will say something like, send 10 tokens to 0x, right? And when it does that one, all you need to worry about is either those tokens got sent or they didn't get sent, right? So I'll change my balance to DeFi contract based on whether or not this worked. If it doesn't work, then I revert my changes. I don't close order book. If the order couldn't be claimed, then I revert my changes here. So I change my orders here, send 10 tokens, and then it works or doesn't work, and I revert the whole transaction to doubt. That's fine. And the whole idea of message passing, it works. I make my changes optimistically and dispatch other messages. And if anything fails, revert the whole transaction, which is actually the proper error handling in like 98% of the cases. And we don't need to add too much more to it. So that's fine. And now what we look in other cases, this is actually create token contract, yeah? With minter. And let's say this address here is, so we create a contract, right? Yeah? So we create this token contract, the minter, and that's great. But the problem is the DeFi contract never knows how to get the minter address. So it needs to know the token address. There's no address when it creates it, right? So you don't have the address. So this then, at some point, needs to say, okay, now format is we call, we get a new address here, and then somehow say, I just got created Okay, so this is a standard call. And this is one case when you really do want to have this back and forth RPC style call, right? It would be nice. So what we've done is basically callbacks. It's a little complex. In this case is actually, we say not very common. It's not uncommon, it's not rare, but it's not very common. So we're trying to make it more optimal. But currently, basically what you have to do is you send a message here to the token contract saying, make a contract and a callback, saying when you're done instantiating, when you finish this contract, call back to me and tell me your address. So that's basically how we're working on it and trying to make better support in the runtime for this flow. And so what that is basically for us, the way it looks like, if you want to see it, is init contract DeFi contract returns init contract message. Then init token contract So that's a flow in 3 steps. Do you see that, Ralph?
Yeah.
So yeah. So we have this 3 step. It could be a promise in another way, another setup. So that's one place we put the limits here. But basically, it's just a little more work. Yeah.
I just want to say that it's a typical continuation passing style. So instead of along with the call, you pass the control flow. So this is not a callback in a classical sense. It's more like a continuation. You just ask, okay, so this is what you're going to do next. The calls doesn't have to be put in a stack. Indeed, they can be arbitrarily routed. So, and I think that's pretty much what you do.
Yeah. So you say, tell this address what your name is. Okay, good. So I'll tell the address what your name is. I'm done. So yeah. I'm going to move a second. It's starting to rain here. Okay, keep talking. Keep talking. Let's turn the video for a second.
Oh, sure. So at least the computation which is going on here is a very typical asynchronous computation. So
exactly.
And what you do here is requires certain computation models. So these calls are not actually calls; they're more like indeed message passing in the continuation. Indeed. Pretty well, but maybe not so common to many programmers today. I think I know that at least coroutines is some form of like coroutines in Kotlin, for example, is an example of simple CPS continuous passing style callback represented in more natural way. And I guess, but I guess for distributed asynchronous systems like the blockchain, especially the network with the CosmWasm, what we have is very. It's not normal to be synchronous. So asynchronous is absolutely expected behavior, but it also means the like. In a typical C or Python or Java program, calling is a very cheap operation, and I guess it's no longer the case for the contracts calling each other. So calling someone else can be expensive. It can fail. It can break for like multiple reasons. So whenever you program, you can always be prepared that this call didn't succeed, and this probably have to be expressed in development tools.
So yeah, we want the language to capture that. So the point is, right now we still asynchronously. We do this mainly for guarding reentrancy in the local model. But with IBC, you actually have these unbounded message passing. So basically, say every contract in IBC basically say, I will commit an intent to call this contract on my blockchain. That then has to get relayed to another blockchain, process another blockchain. Result has to happen at blockchain. The result, the message that when it comes back to us is relayed back to us. That could take 10 seconds. It could take 3 days. I don't know. You are guaranteed to eventually get either an error or a basically not guaranteed. You're guaranteed to get an error or a result back from it as long as the other blockchain progresses. So you have a timeout for 2 days, for example, and you have to see the other blockchain has passed height X. The other blockchain has height X without ever processing your result, then we know your result will never get processed. So we could just call it a failure. So it has this, and that message passing is this message passing. So you return a message to be processed, and then you don't just say, well, if it fails, my transaction rolls back. I actually have to hold intermediate state. It's one level more complexity. So I have maybe this message in process, and I have 20 different messages in process, and waiting for the results, and maybe they get rolled back. So like, if I want to send money from you to some other thing, I say, well, your account balance is reduced in some temporary state, I have this temporary callback, state here. And if the other one succeeds, then great, then I actually remove it. And if I don't, then I return it back to your account because it failed. So that's another level of complexity, which we will be adding in the next months when you have IBC support is getting ready for production. We're still waiting for the underlying IBC support in the underlying SDK. We're working on that one. So we're working on that, but that will have to take the same message processing. So we want to build all the tooling around this concept of sending messages around and not just calling into it, because that we need the conceptual understanding there to be able to build multi-chain contracts. I'm also very curious how you use promises. You kind of have multiple shards and you have promises over that. So I'm curious how you abstract that.
Yeah, so I think promises is a rather weak form of CPS programming. So which paradigms do you actually use in your SDK? Is it actually futures, promises, or something? Maybe something closer to coroutines, or maybe something closer to I don't know, like traditional callbacks. So
it's pretty raw. Return messages. So the interface here, if something like this, handle takes environment, over the call dependencies, environment, the message, and it returns basically a vec of, we call them Cosmos message, more or less. That is what we have. If you're following here, this means we take basically depths is basically our storage access or API access query. Environment is this time I mentioned, the block height, who's calling it, and messages over data. We caught it into it. This is our thing, and return a set. We can there's an error. It's a result, actually, not this. It's something result. It's actually a little more complex than this, but it can error or concede. If it concedes, it returns a list of messages. And that's all you do. So this actor model, right? You turn it. And then the runtime takes messages and dispatches them in the same transaction. And those can also dispatch other ones. It keeps running until it runs out of gas somewhere along the lines, or it's finished all the messages on the stack. And then it's finished, and if everyone succeeded and they've all processed it, then it goes and says, commit this transaction successful. If anywhere along the line it runs out of gas, or one of them says, hey, I don't know how to handle this message, the whole transaction fails. So you can build large systems, but yeah, anything fail, the bigger it is, the easier it's one thing to fail. And then same thing in Ethereum, if you call it other contracts, it runs out of gas somewhere.
So I have two related questions for such a for such a primitives. How do you expect people to reason about them, and how do you expect people to test them for for complex scenarios, like for example when only one of the messages fails and so on? So I think the hardest part about such a vectors would be probably a correct handling of all the possible outcomes, both in reasoning part and in testing part. You can for some systems it's very hard to reason, and sometimes even when you reason right, you cannot test it properly.
Yeah.
That's a problem. How do you solve it?
If one thing fails, doesn't matter, because we said if any fail, we revert the whole transaction. So we make basically a snapshot of the database, and you're working on a cache, temporary database, and temporary transaction, and the whole transaction gets rolled back if any of those messages fail anywhere. So you can write that message saying, I can make these changes optimistically assuming those messages are going to all succeed. Because if those messages fail, then what I did got rolled back. So it happened like I never handled this, right? So that's our assumption. Our critical assumption is if anything fails, the whole thing rolls back.
Yeah, right. But how about composability? So imagine you wrote a contract which has certain set of outcomes, but it is being called as a from some other contract, and so as a result, even if it's the inner transaction is not failing, the whole transaction fails. So to make asynchronous system like that composable, so that we can actually reason about how do I call from function A function B, and so function B always work. Your whole system must be composable. So it's not always that this is like a top level call which is performed on a button click by user. It sometimes may happen as a result of some other software call.
So you're right. That's what you tested. So right now the test we have is basically we launch the blockchain, run those contracts together. And I'm working on now is integration tests, actually even in Rust unit tests, not even WASM. Just run those and say I have these 5 different contracts. I want to string them together in this way, right? I assign these contracts to the addresses, and whether this is malicious ERC20 token contract on the address, or it's a good contract, or whatever else, I can assign these addresses, and then run the test on that. So that's what we're working on right now. One thing we're working on to allow this integration test levels to happen easier for testability of it. So it's not hard. All you basically say is you set up a system with this code and this state assigned to each address. So basically an address, a contract, is a set of bytecode and a set of state, the current state. So you can initialize them all and set the current state of these ones, and then run that. And just have a small mock runtime in Rust, so we can run it in the same test as their code, which would then basically take the messages, redispatch them, handle the errors, roll back the whole thing on failure. So I'm working on that one, and it's definitely testable. It's a little hard to work with some types to make sure they're all nicely abstracted, but the concept's totally testable. What I feel is basically writing it, that people remember how to write it. It's not natural, I guess, if you're used to calling contracts, right? If you're used to calling it, it's not natural. I just want to call this thing. Why I have to return a message that does it thing? It's more of a mental, I think it's more of a buried entry than a reasoning thing. In the end, basically, I assume that all those calls at the end of it basically are just saying, do this if error fail. Effectively, what you have is you just call this message and a question mark operator at the end of it is what you're doing at the end of your code. So I think it's harder to reason about these contracts than calling them. Because yeah, the same call stack, and think of the same call stack. Testing is definitely harder, but you need a runtime for it, and that's one thing we're working on. Now, there's some people have built actually a funny tool called Simulate, which is which will take these contract addresses, and then you can interactively send messages to them and try it out manually. I want to make it more unit testable, very low level unit testable to get full stack traces. But yeah, so we have some tools on that. Right now, most of my tests are basically running in the blockchain and then running Go tests against the Go blockchain with these contracts installed.
And actually, a related question is about debuggability of I think it's a pain point not only like for any particular blockchain, but I think for almost all blockchains suffer from hardness of debugging anything trivial. So, do you take any special measures here in area of debuggability?
I try to make everything testable in unit tests. So I use Rust unit test. So like the contracts, just found out they can compile them as Rust and just run them, and you have full stack trace and everything's beautiful. And then you run it in integrate. You compile it to WASM, and then you run that in a little runtime, and suddenly you get like just VM failed when it panics. So a divide by zero error, which would be actually give you a panic in Rust, will just give you VM fails, because if you divide by zero in VM, it'll just like kill the VM with the trap, and then you don't get a message. You don't know why, right? So the panics and stuff like that inside the WASM become opaque, which is really annoying actually. So I try to debug some of those. And when you see anything like that, all you have to do is, for me, I look for any unwrap statement or anything can possibly panic, and just look for those and have one of those. So I like having the Rust testability. What the other thing we do for testability is we took JSON, which is a much maligned, and actually I personally also malign it, but universal human readable format. So all our messages are in that format, and the return value is too. So if you look at the MSG here and handle, is basically, this is just a serialized JSON. It's an object, actually parse it here, but it's passed over the wire as JSON. And this Cosmos message is another object that serializes JSON. So you could easily add in, and maybe I should just do that as a log level, into the runtime. So every time you call a contract, it says what the call is. And every redispatch can be there. So you could log, say, I called DeFi contract with this set of arguments. It dispatched create token contract with this set of arguments. Get token contract was called this argument, and it called informed created on the DeFi contract with this set of arguments. And you can print that all out. It's not in binary, so it's pretty easy to print in log files. So that's one thing we've definitely had for debuggability. And I turned that off a while ago. It was definitely early on. I was printing a lot of these JSON documents just straight up and reading them as I was running stuff. But since it's been stable for a while and unit test to cover everything, I turned all of it off. But it actually, for these big composition, maybe it's interesting to turn a log level back on so people can run the blockchain with a high level log level and see all those all the messages going back and forth between them and recreate what happened.
Okay, that's that's pretty nice that you have at least this kind of development instruments. On our previous whiteboard session, we were discussing. Just a second. We were discussing their runtime verification as a mechanism of solving at least partially the debuggability problems. So, do you believe in any form of formal verification in your system, or maybe you already do have some additional checkers which simplify the development of smart contracts?
I mean, formal verification is beautiful. I love it, and I think right now, I saw someone talk to people doing that, and it's really cool stuff. Actually, it wasn't directly, but having a JSON parser in there or a Borsch parser, any parser basically blows up the whole thing, right? So for passing 8-byte uint64 over a call, and we can mock that out. But if we're passing large serialized objects and parsing them, the verification includes a serializable parser. So I think it would make sense to take, if you have actually some math, you could take the actual logic inside of it and formally verify some subset of that logic. Again, in Rust, not in WASM, because compiled WASM would include all the serialization stuff on top of it, and the hooks and the memory management, all that stuff. So it seemed pretty hard to formally verify the actual WASM The Rust itself is interesting, and I would definitely love to see if you could pull out like just the functional parts you're doing and formally verify all of those. And maybe that's doable. I'm not sure. Last time I tried doing formal verification stuff was basically with Liquid Haskell and Idris, which is a very different system than Rust. And that's cool. Dependent types is cool. I think it definitely can do a lot of stuff. And found some interesting bugs. You can prove mathematical theorems. A lot of this stuff, however, I feel is smart contracts often more business logic than math. So I can prove I have a B tree that maintains certain invariants. But proving what are the invariants of a Uniswap contract? What are the invariants of it? What must it never fail? I'm not sure. It will go up and down. The price will go up and down. The amount of money reserve will change. Is there an invariant you can mathematically say this invariant must always hold true forever for this Uniswap contract? And then we can guarantee that if the state is in this state and this transition happens, it'll always remain in this state. And those invariants will always be true. So I think you need to find this mathematically. And I think for many smart contracts people are developing, you don't really come from the mathematical proofs. You're not coming from a mathematical object. You're coming from some business domain. And you're trying to turn business logic into a contract, which is fine. That's basically what we're doing. Most of the stuff is building apps and business logic into contracts. And for that, formal verification for me seems overkill. It makes sense if you have a rocket that's going to a moon and there's very clear mathematical proof of what you need to do everywhere. It makes sense if you have a binary tree, or you have a database possibly, which has a very strong controls of what it should do. It should commit in this order. It should never fail this thing. If transactions, shouldn't have two parallel write over the same data without causing some rollback somewhere. The lock should be maintained. So you can have a set of invariants that must hold true for your database. In any possible discorruption state, it should either be able to repair the corruption or be able to detect it's corrupted. It will not blindly, right? So, and there are things like that, like quick test in Rust, which does some cool checks like that to fuzz your stuff, right? Which I think is actually an interesting way of doing some large testing, which I think will cover a lot of what people want to do with formal verification, right? So I think that would be cool. I'd love to have quick check tied into like these basically systems of contracts.
Okay, yeah. So I guess we have very interesting discussion. We try to limit ourselves to usually something approximately like 1 hour to not make people too much bored. So I guess I'd love to say thanks Ethan for coming. Thanks for very interesting intro, for sharing your experience with multi-chain. So thanks a lot.
Thank you for having me here. It's very nice to talk. Yeah.